welcome back to the deep dive. Okay, let's start with a number. A really big, really specific number that, believe it or not, defines reality for us now. 9,192,631,770.
It sounds almost random, doesn't it? But it's anything but.
Exactly. It's not theoretical. It's the actual rhythm, the beat of an electron doing a specific flip inside a cesium atom. And today, our mission is to dive into Jerrold R. Zacharias. He lived from 1905 to 86. A physicist who didn't just build a better clock. He fundamentally showed us what a clock is.
Right. He moved us past metaphor. He revealed that time is rate, simply the measured rate of some stable, repeating motion.
Okay, so let's unpack that idea straight away, the structured motion loop. If everything's motion, what's the cesium atom itself in this picture?
Well, the atom, according to the framework in our sources, is an object, which means it's a really durable pattern of motion. Think of it like a standing wave, but one that lasts.
Standing wave, like a vibration.
Kind of, yeah. A very stable, self-contained vibration. And Zacharias' insight was that the internal rhythm of that specific cesium vibration was the best, most stable beat we could find anywhere.
Okay, so time is the rate of that beat. What about mass, then? The sources link mass to this, too.
They do. Mass becomes resistance to retuning.
Resistance to changing the beat.
Exactly. Or changing its path. How much effort it takes to alter that pattern's rhythm or trajectory. Cesium was chosen because that specific internal flip, that hyperfine transition, is incredibly resistant to being messed with by the outside world. High mass, in a sense, means high discipline for that pattern.
Got it. Now, before Zacharias, timekeeping was... well, it was a headache, wasn't it?
Yeah.
What was the big problem?
The problem was drift. All previous clocks, from pendulums to even quartz crystals, were fundamentally leaky.
Leaky? How so?
They lost coherence. The rhythm wasn't perfectly stable because they were coupled too strongly to their environment. Think about a pendulum clock.
Yeah.
Temperature changes the length of the pendulum slightly. Friction slows it down unpredictably. Air pressure affects it. Our sources nail it. They were loose, leaky oscillators. They just lack discipline.
Quartz was a big step up, though, right? We still use quartz watches.
Oh, absolutely. A huge leap. Instead of a swinging weight, you've got electrons oscillating inside a crystal. Much tighter, much faster.
But still not perfect.
Still not perfect. Quartz still drifts. Maybe a tiny amount, parts per billion per day, but it adds up. Zacharias saw this and said, you know, we need a reference that isn't manufactured. We need one defined by the universe itself.
So the radical step was, let's use the quantum world. Let's use that internal rhythm of cesium-133.
That was the atomic solution. That specific transition, that flip between two energy levels in the cesium atom, its frequency is set by fundamental constants. It doesn't care if the room is hot or cold.
It's incorruptible, basically.
Pretty much. He swapped those leaky oscillators for a super high coherence motion loop, the atom's internal dance, that had almost zero leak. Maximum discipline.
Okay, let's get into the machine itself, because the clock isn't just the atom, right? It's the whole setup designed to listen to the atom.
Exactly. The clock is the machinery that chases the atom's rhythm. It's this beautiful choreography of manipulating motion.
So what are the steps? How does it work?
Okay, first step, state preparation. You take some cesium, heat it up so it forms a beam of atoms. Then you use magnets to filter them so most atoms entering the crucial part are in one specific starting energy state.
You line them up, ready for the flip.
Precisely. Then comes the key part, interrogation.
This is where the microwaves come in, that 9.19 gigahertz frequency.
Yes. The atoms fly through a microwave cavity. The microwaves in there are oscillating very close to that magic.
Yeah.
9,192,631,770 hertz frequency.
And if the microwave frequency is perfectly tuned?
Then the atoms absorb that energy and flip to the other energy state. It's like hitting a resonance perfectly. If the microwave frequency is even slightly off, fewer atoms flip.
Okay, so the microwaves are trying to drive the flip.
That's a good way to put it. The microwave field is the driving motion, trying to sync up with the atom's internal standing wave reconfiguration.
And how does the machine know if it's succeeded?
The third step, detection. After the microwave zone, another set of magnets sorts the atoms based on whether they flipped or not. A detector then counts how many atoms actually made the flip.
And that count tells the machine how well-tuned its microwaves are.
Exactly. It's a feedback loop. If the count of flipped atoms is maximized, the electronics know, okay, my microwave frequency is dead on, perfectly synced with the cesium atom's natural rhythm.
But if the count drops?
The electronics instantly know they've drifted. They automatically adjust the microwave frequency, nudging it back until the count is maximized again. It's a phase-locked loop, constantly correcting itself.
So the machine is always chasing that atomic beat, trying to stay perfectly in step.
Always. The output frequency of those electronics, the one that's constantly being adjusted to match the atoms, that is the clock's output. That's the incredibly stable time signal.
We should definitely mention the pioneers here. Zacharias built this, but he stood on the shoulders of giants, right? Rabi and Ramsey.
Absolutely. Isidor Rabi really pioneered the whole technique of using atomic beams to study atoms back in the 30s. Huge step.
But Ramsey added something crucial for clock accuracy.
He did. Rabi's original method used one long zone for the microwave interaction. That worked, but the resonance signal, the frequency peak you're trying to hit, was kind of broad, blurry.
Harder to tune to, precisely.
Right. Ramsey had this brilliant idea: use separated oscillatory fields. Instead of one long microwave blast, hit the atoms with a short burst, let them drift in darkness for a relatively long time, then hit them with another short burst just before detection.
Why does separating them help? What does the drifting do?
That drift time, that free evolution, is key. It allows the quantum state of the atom to evolve undisturbed. It dramatically sharpens the resonance peak. Think of it like letting a tuning fork ring out for longer. You can pinpoint its exact pitch much better.
A narrower target means you can lock onto it much more accurately.
Precisely. Much less uncertainty. Ramsey's method significantly reduced errors and noise. Zacharias and his team were the ones who really engineered these physics insights into a practical, reliable clock.
And Zacharias didn't stop there. He had this, well, almost futuristic idea even back then, didn't he? The Zacharias fountain.
Yeah, it was quite visionary for the 1950s. He was thinking, how can we make the atoms interact with the microwaves for even longer? Longer interaction usually means better accuracy.
So what was the fountain idea?
Instead of a horizontal beam, you gently toss the atoms upwards through the microwave cavity. Gravity pulls them back down, so they pass through the cavity again on the way down.
Ah, so they get interrogated twice.
Exactly. You essentially double the interaction time without making the machine enormous. Longer interaction time means...
A much sharper resonance line. Better precision.
Bingo.
Slash the line width, boost the accuracy.
Mm-hmm.
The huge problem was back then they had no way to get the atoms slow enough, cold enough to do this gentle toss.
Yeah.
You needed atoms moving at speeds of centimeters per second, not hundreds of meters per second. The technology wasn't there yet.
Not even close. Laser cooling, which makes this possible, was still decades away, but the concept was pure Zacharias.
And it connects back to that core principle from the sources, right? Slowing things down.
Absolutely. Lower the relative motion of the atoms you're measuring allows for higher synchronization density, more coherent interaction, gives you a narrower line, which means better timekeeping.
And today's best clocks are atomic fountains.
They are. The primary frequency standards around the world, the ones that define the second for all of us, they're implementations of the Zacharias fountain concept, made real with modern laser cooling.
Which brings us to that huge moment in 1967. The world officially redefined the second.
A landmark moment. They ditched the old astronomical definition based on the Earth's slightly wobbly rotation. The International System of Units, SI, declared the second to be exactly 9,192,631,770 periods of the radiation, corresponding to the transition between the two hyperfine levels of the ground state of the Cesium-133 atom.
Wow, so time officially stopped being about astronomy and became about atomic physics.
It became a counted beat. Zacharias essentially made the second honest, tying our measurement system directly to a fundamental, unchanging constant of nature.
Okay, now we can really talk about the implications. If time is just the local rate of these motion loops, what does that mean for something like Einstein's relativity? Gravitational redshift, for instance.
It simplifies it, in a way. Gravitational redshift isn't some mystical warping of time itself. It's just that the rate of local motion loops changes depending on the gravitational environment.
So deeper in a gravity well. Slower clocks.
Slower measured rate, yes. The stronger the gravitational convergence, as the sources put it, the slower the local clocks tick relative to clocks higher up.
And these clocks today are sensitive enough to measure this over tiny distances.
Oh, yeah. We're talking centimeters of altitude difference, making a measurable frequency shift. If you carry one of these clocks up a flight of stairs, you can literally measure its rate increasing slightly as it moves up the gravitational gradient.
That's incredible. It makes relativity feel very tangible.
It is. Zacharias' work transformed these once theoretical ideas into practical, everyday physics measurements.
And the most practical application for almost everyone listening has to be GPS, right? Global Positioning System.
Absolutely. GPS is planetary scale choreography, utterly dependent on synchronized atomic clocks.
Why is that atomic discipline so critical there?
Because the whole system works by measuring the time it takes for signals from multiple satellites to reach a receiver. To calculate your position accurately, you need to know the satellite's positions and have incredibly precise, synchronized time signals.
But the satellite clocks aren't in the same environment as my phone on the ground.
Exactly. That's the crucial part. The satellites are moving very fast relative to you, and they're in a weaker gravitational field way up in orbit.
Both of which affect their clock rate, according to relativity.
Correct. Their velocity slows their clocks down slightly, but the weaker gravity speeds them up significantly more. The net effect is that satellite clocks actually run faster than identical clocks on Earth by about 38 microseconds per day.
38 microseconds. Sounds tiny.
Tiny, but it adds up incredibly fast. If the GPS system didn't constantly account for these relativistic rate differences,
Navigation would fail.
it would become useless within minutes. Your calculated position would drift by kilometers within a single day. GPS fundamentally relies on knowing and correcting for these different local rates. It's geometry written in synchronized beats, as the source material puts it.
Amazing. Now, Zacharias also made a big shift later in his career, didn't he? Into education.
He did a major pivot. In the mid-50s, he spearheaded the PSSC Physics Project Physical Science Study Committee
What was the goal there?
to revolutionize high school physics teaching, move away from rote memorization of equations and towards understanding core concepts through hands-on experiments and inquiry.
Which sounds a bit like managing motion and coherence again.
You can definitely see it that way, improving the coupling between the ideas and the students' minds, helping them build a more durable, coherent understanding of physics. Less leak in the learning process, maybe?
Maybe so. Okay, so if we boil down Zacharias' legacy for the listener,
Yeah.
what are the absolute key takeaways about time itself?
I think there are two huge ones. First, time is local because rate is local. Simple as that. Your clock, my clock, the clock on a satellite. Each measures the rhythm of motion in its own immediate environment. There's no single master clock for the universe.
Just countless local clocks, all ticking at slightly different rates depending on gravity and motion.
Exactly. And the second takeaway relates to how we build clocks.
Okay.
The entire history of timekeeping, from water clocks and pendulums right up to today's optical clocks, which are even more precise than cesium, it's all been a quest for one thing: the ideal clock.
Which is?
A motion loop, whether it's a swinging pendulum or an atomic transition, with the highest possible internal coherence, the highest synchronization density, and the lowest possible coupling or leak to the noisy outside environment.
So isolate the perfect beat as much as possible.
That's the game. Zacharias and his group were masters of this. It wasn't flashy work necessarily. It was the quiet heroics of precision engineering. Lower the leak, tighten the loop, let the atom speak.
And that quiet work became the backbone of, well, modern life. Communications, finance, navigation.
Pretty much everything that relies on precise timing and synchronization owes a debt to that atomic discipline he pioneered.
Okay, that's a fantastic journey through his work. So, for our final thought, where does this legacy point us next? We have these incredibly precise clocks now.
Clocks so precise, they can sense tiny gravitational shifts, remember, like moving them up a few centimeters.
Right, so what if we use that sensitivity? Our sources hint at using networks of these clocks.
Exactly. Imagine deploying regional arrays of these hyper-accurate optical or cesium clocks all linked together.
And what would they be looking for?
Tiny simultaneous shifts in their measured rate across the whole network. A common mode blip in timekeeping.
Caused by what?
Potentially by large-scale geophysical events that subtly alter the local gravitational field or cause tiny motions. Things like the strain building up before an earthquake or large underground water movements, maybe even atmospheric tides. Things that create subtle S-gradient waves, changes in the synchronization landscape.
Whoa. So the clock network could act like a completely new kind of sensor, a sort of motion seismograph, detecting reality's rhythm shifting.
That's the provocative idea. Could we use the very fabric of time measurement, refined to an incredible degree by Zacharias' legacy, to sense subtle dynamics of our planet, or even the cosmos that we're currently completely blind to?
That is definitely something to think about. Using time to map motion on a grand scale. What a challenge he left us with.